Okay, so this lecture will be on periodic trends, and it should be all in one lecture. Hopefully it won't be too long. So in intro, we talk about the periodic trends of atomic size or atomic radius, increasing to the left and going down, or conversely decreasing as you go to the right and we go up. So look at fluorine, helium, hydrogen, they're the smallest. We're going to go a little deeper now into how atomic size is affected. We have something called Z effective. Z, if you remember, is the proton, the number of protons, which is going to be the number of positive charges, right? So the effective, however, is the outer electrons do not feel the full force of the protons in the nucleus. They are shielded by the electrons between the outer electrons and the nucleus, all those inner shells and subshells, and also a little bit by the other electrons in the same shell. We also have something called ionization energies, which is the energy required to remove an electron. And this is plural because we have first ionization energy, second ionization, third, etc. And it's the removal of the first electron, the second electron, the third electron. And what those are in relation to the first depends on where the element is in the periodic table and what the orbital or molecular configuration is, electron configuration is after the removal of the first or the second. In other words, if it's at a stable place after, let's say, removal of 2 electrons, like magnesium, you remove 2 electrons from magnesium, it's magnesium ion, and it has a noble gas configuration. So the third ionization energy, the removal of the third electron, would be really high because it doesn't want any more electrons removed. It's in a perfect situation. Full shells, doesn't want to receive or remove any electrons. So that's the logic behind ionization energies. Electron affinity is just like the word says, the affinity towards the desire to have an electron. So if the affinity is high, then that means it has a great desire or affinity for the electron. And that means that once the electron is added, for example, with fluorine, when you add 1 electron, it gets the noble gas configuration. Therefore, that is a lower energy level. The resulting fluoride ion is at a lower energy level. And so the energy that between the 2 stages is released. If I'm going to a lower energy level, something has to happen with that energy that the fluorine had. It's released. So we're going to go into all that. And so that's called a high affinity. A lot of energy is released. A low affinity, either a little energy is released, or you actually had to put energy in to force it to happen. Okay, that's the general statement. So we talk about energy. Everything in chemistry is energy, literally everything. So some of the forces involved. So we still have Coulomb's law, and the force is proportional to the charges multiplied times each other, and inverse related to the radius, the distance, okay? So an electron exists in a particular orbital. That is an energy level that is determined by the energy level of that electron. What is that energy level determined by? It is a combination of factors, but some of the factors are the charge, the positive charge in the nucleus. So the greater the positive charge, the greater number of protons, the greater your force will be. And this is the electron charge. Inverse related to the distance. But you also have a repulsion effect of the electrons between your electron in question and the nucleus. So perhaps it's iodine, it's a really large atom. So the electron, we're talking about one of the valence electrons, it's way out here. And there's lots of electrons, a lot of shells and subshells and orbitals between that electron and the nucleus. So you have a really large R, but you also have this other aspect of the other electrons around. So you have repulsion from that electron and the ones between it. You also have repulsion from that electron and the others in the same subshell. Subshell is S is a subshell, P is a subshell. And the subshells are broken up into orbitals. S only has one orbital. So the S orbital has 2 electrons. It's a single orbital, but P can have 6 electrons, so it's 3 orbitals. And the interaction of all of those electrons can also have an effect on the energy level of the electron. Just some terms here. The inner core, the inner electrons are the core electrons. They're the non-valent electrons. The outer electrons are the highest energy level, the highest N. That means that if I am in period 4, let me get to my periodic table. 1, 2, 3, 4. My outer electrons, and we're not talking about valence, we're talking about the outer, different term but related, does not include the 3 unless the 3 is still being filled. But once I've filled the 3D, let's say I'm looking at selenium over here. This is now an inner core. This is part of the inner electrons, because remember, as soon as you start adding electrons to the D, the energy level drops. It is now lower than the S. So 4S, so let's say we're talking about selenium, 4S and 4P subshells are your outer electrons. The D, once it's filled, becomes inner. Okay? So we have your N number determines outer versus inner and where you are, what shell you're talking about. So that's just terminology. So the factors, again, affecting the energy, you have the nuclear charge, you have what we call shielding by the other electrons, primarily from the ones between the electron we're talking about and the nucleus, all those in between, and the orbital shape, which I'm really not going to go into because that's taking it to another level that we don't need to go into right now. So be concerned about the shielding and the nuclear charge. The shielding, what that does is we take the nuclear charge. So Z for, let's go back to my periodic table. So the Z is the number of protons. So the Z for magnesium is 12. The Z for barium is 56. The Z for bismuth is 83. However, bismuth is really far away from the nucleus, and it has all of these shells between it and the nucleus. It does not feel, the outer electrons of bismuth do not feel the full 83 proton charge. It's diluted in a sense, it's shielded. So what it does feel, and as a way of calculating this, we call it the Z effective, ZEF. It's what it actually feels. It's the effective nuclear charge. And in lab 3, or lab 2, I think, one of your labs, you're going to be calculating this and graphing this. So sublevels, the book talks about sublevels. I call this subshells. So S, P, D, these are subshells. Within your subshells, you have the orbitals. So your subshells become more stable the closer they are to the nucleus. Makes sense. They can feel the attraction, the proton charge greater. The further out you are, the less you can feel it, the lower the energy. So your outer electrons are, those subshells are least stable because they're further out and they're easier to remove. The closer to the nucleus you get, the more those electrons feel that proton positive charge or multiple positive charges, and the harder it is to remove the electron. It makes sense. Think of a really strong magnet and a really weak magnet. when we take into effect all of the electrons involved, you have some shielding because of the other electrons in the same subshell. That repulsion with each other. So in a P subshell, for example, let's look at arsenic here. Arsenic has 3 electrons in the P subshell, 1 in each orbital. Those 3 electrons are going to have a repulsion effect on each other, and they're going to be telling the other ones, get this guy out of here. So these electrons will be easier to remove. They're not only farther from the nucleus, and they have all of these electrons between, let's talk about this electron right here, and the nucleus. You also have this electron with a repulsion effect from this one and this one. So that's going to increase the chance of your ability to remove it. It's going to take less energy to remove that electron. But the greater effect is the shielding from the core electrons, all of your subshell electrons. So it's kind of common sense. So because of this Z effective, the effective charge, the effective nuclear charge, how strongly does the electron in question feel the pull from the center contributes to the atomic size. So again, when we look at the periodic table, because this is periodic trends, as we go to the right, the radius gets smaller. Because when you're in the same period, particularly the first 3, there are no other, you're not adding other inner electrons like the transition metals here. So these are all in the same shell. So you're not adding any underneath, any core electrons. These are all outer electrons. And every time you add an electron, you're also adding a proton. Every step forward is increasing a proton. So you're increasing the proton charge. You're not adding any core electrons. And so all of these electrons are being brought in tighter because they have a greater Z effective. So you get to argon. So as you go to the right, your radius decreases. Your atom gets smaller. As you go down, it increases because, of course, we're adding all of these extra electrons. Remember, these shells are nested within each other. So even though we're not using the Bohr model of concentric circle, it's still a nesting. It's just the shape is very different. We have subshells and orbitals and these things, but you are still putting a huge number of electrons between your outer electrons. Let's say we're going to talk about this. We'll go to bismuth again. We'll talk about this electron. It's all of these shells full of electrons between it and the nucleus. So the Z effective is much less, and it's able to be held more loosely. So it's going to expand more. It's not held as tightly because it's not feeling the full 83 charge. And again, you'll be calculating what that actually is that it feels. So that's how the Z effective contributes to the atomic radius. The trend is still the same that you learned in intro. Decreases to the right, gets smaller, increases as you go down. So we're getting bigger as we go down here. And here's a general representation. And you can see over here with groups 1 and 2, the difference in size is more noticeable than as you go further right. Because these still can feel the proton charge greater. And you don't have the repulsion effect that you do over here, which is keeping them away from each other. So, but you still can see the general trend of size. And that's the point of this. We are decreasing as we go this way. So even though we're increasing down, it's still, these guys are going to be smaller than these guys. So when we're going to rank elements, not any ions or anything, just elements right now, in decreasing atomic size, you're going to go according to the periodic table. So we have calcium, magnesium, and strontium. Here's calcium here, here's magnesium here, and here's strontium. So obviously the magnesium will be smaller than the calcium, which is smaller than strontium. Or You can say it the reverse way. Strontium is larger than calcium, which is larger than magnesium. So that follows the trend going down a group. The next is potassium. I don't know what Ga is, like gallium, I think, and calcium. So here's potassium and here's calcium, and it is gallium. So this is going to be the trend going along a period. It's smaller to the right. So gallium is going to be smaller than calcium, which is smaller than potassium. And in fact, here's potassium here, here's calcium here, and here's gallium here. So you can see that. And then there's your trend. So that's going across a period. Rubidium, bromine, and krypton. Well, here's krypton, and here's, is it bromine? Yeah, bromine. Yeah, bromine, rubidium, and krypton. Here's krypton, here's bromine, and where's rubidium? There's rubidium way over here. So rubidium is going to be the largest. It's not only further left, it's down the next period. So it's further left and at a higher period. A greater N number. The greater your N number, the further you are from the nucleus. That's what N means, one of the things. So that's going to be larger, and then we're going to go bromine and krypton because now we're going trend to the right. Right? And then there are your explanations. Okay, what if we look at nitrogen, phosphorus, oxygen, and sulfur? You're looking for the smallest atomic radius. So here's nitrogen, oxygen, phosphorus, and sulfur. Excuse me, I just sneezed. Pardon me. Okay, well, the ones at the higher period are going to be bigger than the two on the smaller period, than in period 2. So period 3 atoms are going to be bigger than period 2. So we're going to eliminate phosphorus and sulfur. That leaves nitrogen and oxygen. Well, we're going to go to the right. It gets smaller. So oxygen is the smallest, following that logic. So the answer would be oxygen. All right, so that's size. Ionization energy is the energy required to remove an electron. And its official definition is the complete removal. So it is completely out of the area of being influenced by the nucleus. Because remember, there are infinite energy levels for an electron to be excited to. So this has to actually be removed far enough that it feels no more influence of the nucleus. So complete removal of 1 mole of electrons from 1 mole of gaseous atom or ion. So that's the official definition. Obviously, atoms with a low ionization energy, which means it takes very little energy to remove electron, form cations. Makes sense. That's why they form cations. And atoms with a high ionization energy, it takes a lot of energy to remove the electron, as a rule, form anions. And the energies decrease down a group because we're getting bigger. The larger your atom gets, the easier it is to remove an electron because it's feeling the effective charge of the nucleus less and less and less. So these are easier to remove than this. And the other trend is it increases across a period because, of course, we go across a period. Your element is getting smaller, so it's going to feel the force of the nucleus, the protons in the nucleus more. But also, as we go closer to the right, the addition of electrons will contribute to the formation of a noble gas status. So there's, I like to talk about these as human terms. It doesn't want to have electrons removed. It wants to have them added so it can become noble gas status. So there's some logic to it there. There is a very interesting trend. Notice, so hydrogen, no, we'll just skip hydrogen. Lithium, 520 kilojoules per mole to remove an electron because it removes 1 and it's at noble gas status. So that's considered a low ionization energy. Beryllium is higher. But once you get past, this is a filled S shell. Now boron is actually a little bit lower energy because once you remove 1 electron from boron, you have a filled shell state. So the trends also follow the stability of what happens when the electron is removed. So as we go up, this is the p orbital. So here's boron, copper, nitrogen, oxygen, fluorine, neon. As we go up the first 3 orbitals of the p shell, subshell, your ionization energy increases, right? It's getting harder and harder to remove an electron as your element gets smaller. However, look at this, between nitrogen and oxygen, all of a sudden it's easier to remove an electron from oxygen than from nitrogen. Why? Let's go to the whiteboard and I'll show you. Whoops. And it has to do with the stability of your element after you've removed that electron. So nitrogen is 1s2, 2s2, 2p3, and oxygen is 1s2, 2s2, 2p4. So I'm going to skip the 1s2 right now. I'm just going to talk about the valence electrons. So there's my 2s orbital. This is the orbital configuration. And here are my 2p. Here's each orbital. Okay, so we label the bottom of it. Both of these have the filled, that's not going to work, the filled S. Now nitrogen, we enter 1 electron in each empty orbital. That's the lowest energy configuration. Now, if you remember, a half-filled subshell is stable. The next more stable, or the more stable configuration from this is a filled subshell. So this is the next most stable configuration. Now, oxygen is 2p4. So now we're going to start doubling up. There's oxygen. When I remove this electron from oxygen, the result is the half-filled shell, and that's more stable. That's why the energy, the ionization energy for oxygen is lower than for nitrogen, because the result is a more stable configuration. And you can see this trend throughout. You see it again with the phosphorus, and then energy drops back down for sulfur. So it's easier to remove the electron from sulfur than from phosphorus. It's a little more confusing when we add the F intertransition metals. So let's just stick to the first few periods for this trend, but it's definitely there. And this is, this slide shows it. So this is ionization energies. There's helium. Helium, of course, is a noble gas configuration, so it would be very hard to remove an electron from that. So it's a high ionization energy. You have to put that much energy into it to remove an electron. But now we go back down. Here's lithium. All right, if lithium removes 1 electron, it has this configuration, so it's a very low ionization energy. And this is beryllium. It's a little harder to remove this because it only gives you the lithium configuration. It prefers, but it's still pretty low. That's considered low. Now we start with the P subshell. So this is boron, and it drops back down because, again, if you lose 1 electron from boron, you get a filled shell configuration. That's stable. There's carbon, and here's nitrogen. Here's your oxygen dip, because losing this electron will give you the nitrogen configuration of a half-filled subshell, half-filled P subshell. And then, of course, the closer we get to the noble gas configuration, the higher your ionization energy goes. This is first ionization energy, removal of 1 electron. We start a new N number, a new period, and once again, it drops back down because removing 1 electron will give each of these a noble gas configuration. And sure enough, we see lithium, sodium, potassium, etc., with generally exist as a 1+ cation. So this trend follows along. It gets a little messier when we get into the D, add the d orbitals and add the F. So recognize it more for the first 3 periods. But so you always want to look at, when you're wondering what will be the energy to take this action with an atom, whether you're adding an electron or removing an electron or removing 2 electrons, look at the result. What will it give me? Will it give me a more stable situation? If it will give a more stable situation, it's going to be a lower, either a lower energy needed to remove that 1 or 2 electrons, or a greater affinity to receive an electron. So you always want to look at what's the end result. So if we're going to rank, and this, we show a first ionization energy with a subset 1. Second ionization energy would have a little 2 down here. So that's removal of the second electron, not 2 electrons, but the second. We talk about each individual electron individually. So if we're going to rank these, we have krypton, helium, and argon. Here's krypton, helium all the way at the top, and argon. The larger your element is, the easier it is to remove an electron. So krypton will have a lower than argon, which is lower than helium. Now, none of these are going to have low ionization energies because they're all noble gases. But here's krypton, here's argon, and here's helium. So the larger you go, look at how, like here's xenon, it's equivalent to, it's actually lower than the oxygen here. Krypton looks like it's equivalent to between the nitrogen and oxygen ionization energy. So it really does make a difference. The size of the element makes a significant difference. Tin, beryllium, and I forget what SB is. So here's tin. Go back, what was that? Te, beryllium, and SB. Here's SB, here's tin, and here's beryllium. Okay, so this is these 3 elements. And so as we go to the right, your ionization energy will increase. Now, again, that trend I talked about with a half filled full, that's more in evidence in the first, period 2 and 3. So it wouldn't really apply here because at this point we have the d orbitals involved as well. So just keeping with the strict trend of going to the right, tin should be lower, excuse me, than antimony, than tellurium. And that one's not even listed here. But anyways, it would be just the trend going, the ionization energy increases as you go to the right. Potassium, calcium, and rubidium. Potassium is here, calcium is here, and rubidium is down here. So rubidium is higher period number or end number, and it's further left. So that would have the lowest ionization energy, and then potassium, and then calcium. Oh, I think I said that backwards. Calcium has the highest ionization energy. It's further to the right. Potassium has the next highest. Rubidium has the lowest ionization energy because it's larger and it's further to the left. Okay. Iodine, xenon, and cesium. There's xenon, iodine, and where is cesium? Okay, I know where it is, but I can't find it. Let's see. So xenon obviously is going to have the higher ionization energy. It's a noble gas. It's further to the right than iodine. And for some reason, I cannot find cesium. Further to the left in a higher period. So when you find cesium, further to the left in a higher period. Oh, that's why, because it was, okay. So cesium is here. So that is going to have the lowest ionization energy because it's at a higher period. So it's larger and it's further to the left than iodine, than xenon. All right. Nitrogen, phosphorus, oxygen, sulfur. Once again, we had that question for radius. And so the answer should be the opposite. The lowest ionization energy means it's easier to remove nitrogen, phosphorus, sulfur, oxygen. It wouldn't be nitrogen or oxygen because they're at a lower period number. So of the sulfur and the phosphorus is further left, and sure enough, it does have the lowest ionization energy. Whoops. Actually, no, that's not correct. So this is because this is in the third period. So this still follows that half-filled subshell. And if you look, the sulfur is lower than phosphorus because when we remove the electron from sulfur, we are left with a half-filled subshell, which is more energetically favorable. So in this case, because of that rule, and we're still in the first three periods, the sulfur actually has the lower ionization energy, just a little bit, because losing this will give you a more stable electron configuration. So there's an example to take your time when you get these questions and think them through. Don't answer them too quickly or you'll make mistakes like I just did. Yeah, that one's common sense. So this is just shows you the trends of the ionization energies. And if you notice, whenever you have a fold shell, so this is the first ionization energy, there's your second, there's your third, etc. When you break into the core electrons, which is the electron configuration of the inner electrons, no longer the outer higher energy, your ionization energy really jumps up. So this is when you're disrupting a noble gas configuration. You see a huge leap in ionization energy, and it makes sense. So the largest jump in ionization energy for aluminum, well, we know that aluminum exists as a 3+ ion, right? So this is easy to remove because it gives you a filled shell. But the fact that we know it exists as a 3+ ion, once you remove these two, you're at a neon configuration. That's the one that's going to be hard to remove, the fourth electron. And if we look at this table, aluminum's not on this table. But the largest jump would be the fourth ionization energy, removing the fourth electron. So between the third and the fourth would be your biggest jump. Fourth ionization energy would be much, 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 much greater than the third. And so that would be your leap. Okay. Opposite to ionization energy, you have electron affinity, and it's just like it sounds. The affinity means it wants electrons. So this is the tendency to attract electrons. Again, the official definition is the energy change when 1 mole of electrons is added to 1 mole of a gaseous atom or ion. With a low affinity means it does not want electrons. If it doesn't want them, it tends to form cations. It wants to give them up, not take them. A high electron affinity means, yes, it does want electrons, and they tend to form ions. So affinity is generally given with a positive or a negative sign, and that refers to the energy released or forced. Ionization energy is always with a positive sign. There is always energy required to remove an electron, but sometimes it's very, very low, and it's made up by the new situation. Electron affinity can be positive or negative because remember, here's fluorine, the element. Once you add an electron to it, the result is a lower energy level. We say that all the time. It is a filled subshell. When I say it's a lower energy level, where did that energy go? It was released. Just like you have the delta H for enthalpy of a reaction, exothermic versus endothermic. A negative delta H is an exothermic reaction. It is released. It's a product. The same concept is here. If you have a negative EA, energy is released. So the higher the negative EA, the more energy is released. That means the more stable the product is, the end result, the greater the affinity. So it's a very logical thing. The trend is not nearly as clear-cut as for ionization energy. So you just have a general trend. So the general trend, but again, for affinity, it's the examples you're going to be given to answer are going to be really clear-cut because there are a lot of exceptions to it. It's a little more complicated, but in general, the smaller your atom is, your element, the greater, because it's going to feel the effective charge more, right? So the greater the affinity. So as you go up in the periodic table and to the right, which fits with the smaller radius, the greater the affinity. Remember, nonmetals prefer to be anions, so obviously they would have a greater affinity than metals, which tend to be cations. Your atomic size follows the same trend. This is written in reverse. Increases, increases, or you could reverse these arrows and say, just like this, your size decreases going up and decreases going to the right. Gets smaller as you go to the right, gets smaller as you go up. The ionization energy is the opposite. The smaller your atom is, the harder it is to remove an electron, so the greater your ionization energy is, the same going to the right. So make sure you know these general trends. The last thing is ions. Now, the size of an element follows that specific trend going up and going to the right of the periodic table. But the size of an ion depends on how it got there. If you remove an electron, it significantly decreases the size of that element. If you add an electron, it significantly increases. When the ions, if you remember, produce noble gas electron states. Where's my periodic table? Here we go. So when you have the same electron state, for example, potassium ion, potassium plus, is the same electron configuration as argon. We say that it is isoelectronic with argon. Chloride ion, it added an electron. It is isoelectronic with argon. However, they do not have the same size. The chloride ion, the argon element, and the potassium ion all have the same configuration, but the chloride ion is going to be bigger than the argon because it added, and so it significantly increases. The potassium is going to be much smaller because it significantly decreases when you lose an electron. So the trend is when you have an isoelectronic series and you're told to rank them by, rank them by size, that means they have the same number of electrons. So anything that got there by losing electrons is going to be smaller. And the more electrons you lose, the smaller it is. The more electrons you add, the bigger it is. So keep in mind that trend. Here's some examples that show you just how significant this can be. So the sodium element is 186 angstroms. It loses one electron, it's 102. Now, unfortunately, this doesn't show us a noble gas. That would be nice if it did. The fluorine element is 72 angstroms. When it adds an electron, it's 133. So fluorine is isoelectronic with sodium, but this is 133 angstroms, this is 102. And yet they have the same number of electrons, the same configuration, the same filled shells and subshells. Because this still has a greater number of protons, so it's going to pull in tighter than this. Aluminum the element is 143 angstroms. It goes down to 54 when it loses its 3 electrons. And yet it is isoelectronic with magnesium 2+, sodium, with all of these have the same electronic structure, yet look at the differences in their size. So remember that trend that if your configuration got there from gaining electrons, the more it gains, the bigger it is. If it got there from losing electrons, the more it loses, the smaller it is. So for example, calcium, strontium, and magnesium, how would you rank these? We have to look at, they each lost 2 electrons. Where's my periodic table? So calcium, strontium, magnesium, they're all in the group 2A. Go back down. And they all lost 2 electrons. But strontium has more protons, doesn't it? But magnesium started out smaller to begin with. So your logic here is they each lost 2 electrons. Therefore, you're going to follow the trend of the periodic table, which means the ion, if they all have the same, lost the same number of electrons, this is bigger than this, which is bigger than this, because this still has all these subshells behind it. So if you have lost the same number of electrons and you're in the same group, you will follow the normal trends of the size trend. There's my questions. I should have put one more periodic table down here. So potassium, sulfur, and chloride, however, this lost 1 electron, this gained 2, and this gained 1 because, so here's your potassium. So your potassium ion goes to argon, isoelectronic with argon. Chloride ion, isoelectronic with argon. And sulfur, sulfide ion, is isoelectronic, which means the one that gained the most electrons, sulfur, is larger than chloride, which is larger than potassium. Potassium is going to be pretty small. Let me see if that's on here. So there's potassium is 138, chloride is 181, and sulfur is 184. So there's not much difference between sulfide and chloride, but it still is there. And then gold, 1+ versus 3+, the more electrons you lose, the smaller your radius is. So gold loses 1 electron is going to be still larger than gold losing 3 electrons. Again, that's kind of common sense. Okay, so those are the trends, the periodic table. A lot of it is just really common sense. Again, think about, especially when you're looking at electron affinity and ionization energies, plural, look at the result and then determine, is it more stable? Like, what does it do to the stability? And that will help you determine the level of affinity or the level of the ionization energy. Okay.